Um, can I have to change the slides?
Just tell me.
Okay.
Sorry.
We can have a pointer though. Did that here? Did that help?
Oh, nice. Okay, thank you.
Okay, welcome for this new seminar. Today we will have the talk by Giorgos Michailidis from Aristotle University in Thessaloniki in Greece. And he will talk about high resolution study of Blazar TXS 2013+370 and B, a space technology and research student team. Giorgos will be properly introduced by Tanya.
Yes. Hello, George is a master student at Aristotle University of Thessaloniki in the computational astrophysics. And the last months we're working together in his thesis, and we're working studying the Blazar TXS 2013+370. George, the floor is yours. Let us know more about
hello from me. Thank you for being here. As you shared, my presentation is divided in two parts. The first one is about my master thesis. We start with high resolution study of Blazar TXS 2013+370. And BIM, an aerospace student team based in the Aristotle University of Thessaloniki. You will see it in the slide. So I'm going to start to talk about my master thesis. I'm going to talk about what an AGN is, so we can understand what the Blazar is, about the gamma ray flare that we observe in these objects, the observational techniques that we use to observe them, the VLBA. I'm going to talk a little bit about the source, some properties of the source, and how we do the data analysis, the calibration, and the imaging. And then I'm going to talk about BIM. I will present to you some of the projects that we did throughout the years. You can see it? Okay. So I'm going to start with my thesis. Okay, so to understand what the Blazar is, we have to understand what an active galactic nuclei is, or else AGN. So AGNs are the most luminous objects in the universe, emitting radiation across the whole spectrum. And to simply understand what an AGN is, you have to take a galaxy, put at the center black hole, and throw some gas that can occur through a disk around the black hole, and then you have a center that's active. Now, 10% of the galaxies that we observe in the universe have active galactic nuclei in their center. Some of them, they can form jets that we can observe on scales of astronomical units to megaparsecs. So here you can see the anatomy of an AGN. You can see the black hole that powers the whole phenomenon. You can see the accretion disk, some gas clouds that they can also feed the black hole along with the accretion disk. You can see the torus, which is actually dust that absorbs light from the AGN, and it makes it impossible to see. It makes the AGN invisible to see it when we view the galaxy edge on. You can also see the twisted magnetic field lines where the particles are trapped and they emit synchrotron radiation. Basically, this is the jet. You can see the radio loop where the jet ends and it's far away from the center of the galaxy. And when we see this jet, when this jet aims towards Earth, we name this object a Blazar. There are two types of Blazar, the radio loud and the radio quiet. The radio loud have very strong radio emission. Blazars are in the radio loud category, where they have some subcategories, which is the B-LAC objects and the optically violently variable phasers. The difference between these two is that the B-LAC objects have weak or no emission lines in their spectrum, and this is because their jet is very powerful and overwhelms the spectral lines that come from the surrounding dust, while the optically violently variable phasers have strong emission lines, and they are more luminous they're more luminous than B-LAC objects. And a subcategory of the OBV quasars is the flat spectrum radio quasar, which is the source that we study in this project belongs to this category, and we're going to see some information later. Here you can see that observing the AGN from different angles, we see different phenomena, and we name this, we give another name for that comes from the same object. Now, some open questions that surround AGNs, the jets of the AGNs, are what are they made of? How do jets form? Why some AGNs have jets and others don't? And the question that we are trying to answer in this project is where and how the gamma rays are produced. Okay. Now, gamma ray telescopes can't help us answer this question because they can reach the resolution that we need to find the location region of the gamma rays. But there are some scenarios that answer to this equation. And the first one is the parsec scale emission, where the photons come from far away from the black hole inside the jet using the self-Compton radiation. And we have the sub-parsec scale, where the emission region is closer to the black hole, and the dominant photon field is from the inverse Compton, and the photons come from the BLR integration disk. We have a scenario that suggests that there are multiple emission regions, which means that the photons come from both far away from the black hole and near the black hole. VLBI can help us resolve these regions close to the jet apex, and this is because we can create radio maps of the source with very high resolutions, and can help us investigate the origin of the gamma rays. Now, what is VLBI? VLBI comes from the name very long baseline interferometry, and the reason that we use it is because we need more resolution. Radio telescopes, they collect radio waves using an aperture of a certain size, and the resolution that you can achieve comes from this equation. So if we say that we want to observe a hydrogen cloud at 21 centimeters, and we want to achieve a 1 second resolution, the aperture must be from this equation almost 43 kilometers, which is impossible. So the solution is to use a pair of antennas to synthesize an aperture of that size. So in this figure, you can see the simplest interferometer, which is consists of two antennas. And what an interferometer does is to measure the spatial coherence function of the radiation field. So basically, each antenna measures the electric field in its location, sends a signal to the correlator, and the correlator calculates the coherence function of the two waveforms, which is actually a time average of the signal. Now, this is a function that we call spatial coherence function, and using some math and some assumptions, we can show that these functions can be calculated from this integral, where here we have the intensity from the sky and an exponential that shows us that this function, it depends on the separation vector of the two antennas and not from the absolute vectors of each antenna. So this means that we can measure this function just by holding one antenna fixed and moving the other one around it, and we don't have to measure it in every pair of points. This function is also called a spatial autocorrelation function of the radiation field, and it's all we have to measure. And this is because if we define two appropriate coordinate systems. One to express the baseline, the vector of the two antennas, and one to express the source brightness distribution. We can show that the previous equation can be rewritten like this, which is a Fourier transform, and with an inverse, we can take the sky intensity just by measuring the spatial coherence function of the radiation field. Now, this is how an interferometer works, and the difference in VLBI is that the antennas are very far away from each other. They can be very different continents, and this is what actually gives us the longest baseline, which results in a better resolution, because the resolution, it depends on the distance of the two antennas. Okay, now a little bit about the source. Our source is a Blazar, located in the Cygnus constellation. It's very far away, as you can see here, and it's very active in radio and gamma. You can see an image that was created using data from the Mojave program at 15 gigahertz. The galaxy have a supermassive black hole, and it hosts a jet that points directly towards Earth. Now, in the paper that my thesis is built on, Traianu et al., they had some data sets in 3 frequencies. The first one, you can see the light curves here. The first one is in the gamma emission. Then we have 1 millimeter from the SMA interferometer, and 15 gigahertz from the overall. So you can see that at 2009, the source gave a gamma ray flare, and after some time, there was also radio emission. And in this work, they tried to find if there is a correlation between these two emissions. So they did a DCCF analysis to show, and they show that there's a strong correlation between these two emissions above the 99% significance level, with gamma rays leading the activity for 45 days. Okay, now using this data, they do a kinematics analysis at 43 gigahertz, 86 gigahertz, and 15 gigahertz. And after 1 year, the flare, they saw that there was a new component in the jet, which indicates that the location of the gamma ray is very close to the jet apex. And using this kinematic analysis, they took the plasma speed at these scales, and using this equation, the time difference between the emissions and the velocity, they were able to find the distance between where the VLBI core was and where the gamma ray emission took place. So they found that the dominant photofield was the external Compton, and the photons came from the dusty torus or the broadline region. Yeah. So for our project, the source at 2020 started to have a gamma ray flare, a new gamma ray flare. You can see right here that the gammas are going up, and also you can see that the Jansky in radio, they also increased. So they did a proposal to take measurements at 3 frequencies at 22, 43, and 80 gigahertz using the very long baseline array plus Effelsberg. Their data with almost 8 hours of observation, and adding Effelsberg to the array allowed us to have an angular resolution of 0.1 milliarc seconds. Now, Taking this data, we did a calibration in apes, which is actually a difficult procedure to do in VLBI, especially when you go to higher frequencies. The atmosphere starts to corrupt the signal, so it makes it even more difficult to correct it. You can see here how was the phase and the amplitude before the calibration, and how we correct it with apes to get this result. Yeah. Now, having done the calibration, you can move to imaging, where you can see how the source looks like at 22 gigahertz and 86 gigahertz. This is at 15 gigahertz, 6 months after the flare. This is from the Mojave project. We don't have actually an image at 43 gigahertz because we faced some problems that we solved yesterday, actually. So yeah, instead we can show you at 15 gigahertz. Now you can see here how going to bigger frequencies, how closer we can go to the jet apex, how closer to the start of the jet, we can see to the start of the jet. Okay. Now, the next steps are a Gaussian model fitting in order to obtain the spectrum of the flare, a polarization image to see the local magnetic fields in the jet and how they behave during the flare and after the flare, and the Faraday rotation measurement to see if there is a twisted in the magnetic field lines. Now, of course, this is not enough. So we have some data sets from the GMV, which is monitoring the source for 2 years at 43 and 86 gigahertz. And we're going to use this data to do a kinematic analysis on the jet, monitoring of linearly polarized emission variability, and to see the spectral evolution of the flare. Okay, so now I'm going to the second part, where I'm going to talk about BEAM. BEAM is an aerospace student team in the Aristotle University, which I'm a member of it. Next slide. Now, BEAM was founded in April 2018 by a group of engineering students that wanted to participate in the Bexus Rexus campaign that is organized by ESA and SSC. SSC is the Swedish Space Corporation. Basically, it's a space campaign that gives the opportunity almost every year and a half to student teams across Europe to design a space mission and launch their experiments to space. And they can do that using either a stratospheric balloon, which is called Bexus, or a one-stage sounding rocket, which is Rexus. Now, each platform gives very different conditions about the experiments. Bexus flies to the stratosphere and gives a 5-hour flight to almost extreme low temperatures at very low pressures, while Rexus gives 10 minutes, almost 10 minutes of microgravity due to its parabolic trajectory. So BEAM's first participation was the SAID experiment. You can see it here, flying the stratosphere, where the team designed a mechanism that could upload a helix antenna during the flight. So here you can see the antenna hanging out from the gondola of the balloon. And I think it's almost 30 kilometers here above Earth. After SAID, we had LIGHT. LIGHT was more of a software project where the team designed a navigation helmet for astronauts to the moon in order to help the astronauts with their task, everything that can make the life of an astronaut on the moon easier. After LIGHT, we had EcoWise. It was BEAM's second participation in the Bexus campaign, and it was the first experiment that introduced me to the team. So I'm going to talk a little bit about EcoWise later. And then after EcoWise, we had LISER, where I was also a part here, where we created a CANSAT, a 3D printed, very small satellite where we upload a gamma ray detector, very small gamma ray detector, with the idea that this CANSAT could be helpful in space exploration missions by throwing it to a planet and determine if this planet is suitable for people to live, depending on the gamma ray emission there from isotopes from the ground, from the cosmic rays, because the analysis that we did was to return a measurement that could tell us how much radiation humans would absorb if they stayed at that place for 1 hour, 2 hours, 3 hours. And then there was Dropstar, which was Beam's first participation at the Rexus campaign, where the team studied oil droplets in microgravity using a very special mechanism that they developed in the chemistry lab of the Aristotle University. Unfortunately, I don't have much information here because I wasn't a member of the team. Here you can see actually the mechanism of the Dropstar being on the rocket. And here is the Bexus at the night that the SAID was launched. Now, for the EcoGuys is called Ecological Computations with Low Cost Setup. The idea that we had for EcoGuys was to reduce the overall cost of a stratospheric balloon for atmospheric measurements. EcoGuys was an experiment that did some atmospheric measurements, and apparently, if someone wants to do atmospheric measurements in the stratosphere, must buy very expensive sensors, for example, to measure CO2, ozone, and these sensors can cost up to thousands of euros because they have to operate in very hard environments. So if you add at this cost the overall cost of the mission, the balloon, the helium that you need to fill the balloon, everything, the cost reaches thousands of euros. So we are like, why we can buy cheap sensors that are designed to work in the ground in prices of 2 to 50 euros and make them work up there. So we did it. We designed a box that using some tubes and heaters and the heat from the electronics, we were able to create inside the small box suitable conditions for the sensors to work as they must, because these sensors freeze. They don't return anything, any measurements. You can't see anything if they freeze. And actually, outside we have minus 60 Celsius, and inside the box we have like 30, 40 Celsius. It was really hot. Now, you can see some images with the experiment being placed in the gondola. You can see the preparation, how they take the gondola outside to go to the launch pad, where is the balloon. This is some minutes before the launch, and you can see the landing, which the experiment actually falls from 27 kilometers, and we had a 5-hour flight. Again, now here you can see some images during the flight. These were taken using a camera from another team that they wanted it to observe the experiment. EcoGuys somewhere right here, so it's not visible. This is in the stratosphere, 27 kilometers. And being in northern Sweden, this was our view every night at the Strange Space Center. Now, ASTRO is the only active project of Beam right now. Actually, it's the first project that doesn't participate in any campaign or competition. It's an idea that we had with our professor in the university. The idea is to design and construct a 5-meter radiotelescope for the university with a range of 1 to 20 gigahertz or even 50 if it's possible. So the idea came during our radio astronomy lectures, where our professor was like, unfortunately, we don't have a radiotelescope here to see everything in action. And we were like, okay, we have a team that do these kind of projects. Do you want to build one? And he was like, say no more, let's go. So we started this project. It's going to be a tool that will be used for the student needs in the physics department in the university, and of course, it will be open for use from every university in Greece. Now, the project is still on the papers, so I don't have images to show. But right now we have subsystems that are working in the antenna. We have the mechanical, electrical, and robotics that they are designing the antenna. Robotics actually has a task that they're going to make the antenna to rotate and to be able to use it. How can you say that? From far away, remotely. Yeah. So we have the science and the software. Software, they are developing some scripts, so you can do data analysis with the data and some graphical interfaces. So people that don't know programming, they can use the telescope and do the data analysis by just pressing buttons. And we have the science. Science has two tasks. The first is to create a catalog with all potential targets of the telescope, and second catalog that they will have all the physics behind these sources, how they determine that it's a potential target and stuff like that. And of course, we have the marketing for the outreach to the people and for sponsors. And here you can see some sources that the science subsystem right now try to find. We have hydrogen line 21 centimeters. This is the main source that we're aiming. Synchronous kilotron thermal radiation from solar system bodies like Moon, Jupiter, Venus. And of course, we have some masers and closer to galaxies if it's possible. Actually, these two sources are a little bit questionable. But here, you can see an example of some masers that are considered for observation if we were able to reach the 50 gigahertz. We can move. So our team structure, of course, we have our supervisor professor, Dr. Pantelis Papadopoulos, here, he's here, who help us with everything we need, give us advices and tell us what are the next steps to do. We have the project manager that organizes the whole team. We have the project scientist, who helps the subsystem with more practical tasks. We have our mentors, PhD students, postdocs, colleagues of our professor that help us with questions and train us during training weekends that we do throughout the semester. And of course, the subsystems that take all this information and put it in an action. So right now, currently, we have 40 members. And that's it. Thank you.
So now the talk is open for questions. Okay.
I have many actually. I've been great time.
Amazing.
I can ask a few and there are more. Right. So in the first part of your talk, the VLBA stuff, you mentioned. I mean, I have no idea of this topic. Okay, I'm completely alien, but you mentioned that there are 10% of AGNs.
Yeah.
Isn't that too small? I mean, I
Yeah,
thought that every
blazars
galaxy
are
had a
even more.
black hole in the thing, and it was more or less active, or it's only like the spiral. I don't know. 10% to me sounds small.
Yeah, it's very rare. And blazars are even rare.
A blazar I understand because it's
Yeah.
It's an observational bias, and I want actually my follow-up question is that 10% an observational bias, or is it there is a physical reason why we only have like 10%?
I think it's observational. How can I say that? It's in the observing universe, you know, that we have detected so little. I don't know if it's something physical, but
Right.
yeah.
No, I mean, again, I have no idea of this topic.
My understanding is that only around 10% of the supermassive black holes develop powerful radio jets.
Oh, right.
Oh, there are also studies that AGNs generally is 10% out of all galaxies.
Right.
Some of them don't have jets.
Yeah.
But they do have a black hole.
Yeah.
And jets,
Supermassive.
and jets are
Yeah.
Jets are produced in 10% of the AGNs.
Yes.
Oh, right.
AGNs are a small percentage of the entire population of supermassive.
Right. Okay. And then a follow-up question, if I may, because you connected. You also mentioned that these AGN jets
Yeah.
may come from accretion powered disks.
The jet?
Yeah.
No.
Maybe I missed that.
Could be.
Where is it coming from? The jet.
It's an
From the
open
AGN.
question.
From the
It's an open
accretion disk.
question.
Yes.
That,
Not only, actually, this is an open question.
that was my follow-up question because I do protostellar jets. So I study how the stars form, there is a star in the middle, there is an accretion disk, and there is a jet. Actually, you can make a lot of similarities.
Yes, yes, yes.
And my question is, what else can we produce? Because in our case, it's mostly only the accretion disk. What else can produce this jet?
Anchored magnetic fields in the black hole's ergosphere can take a fraction of the material that falls into the black hole and launch it as a jet. And actually, yes.
Without the need of the disk.
Yes.
No, but you need material, no?
Yes.
I mean,
That was my point. So you need
you
the
need
disk.
magnetic fields, you need
Accreting material.
Yes.
Right.
material, and you need the gravitational power
Right.
of the supermassive of the black hole.
And actually, this is a long-standing question, and we are not sure how the jets are launched.
Right.
But we have some theoretical scenarios. One is the black hole SNIEC that
Right.
supports
It's
the
okay.
launching from the black hole ergosphere, and the black hole PENA that supports the launching from material from the accretion
Right.
disk. Again, the anchored magnetic fields can elevate material and launch jets. But observationally, we can see also a combination of two. The C-spine anatomy of the jet
Right.
supports that maybe both mechanisms, or even more that we don't know, are can take place.
I'm obsessed to trying to make these similarities
Yes.
in the two worlds
It's
because I think
beautiful, yeah.
it's just, I mean, to me, when I listen to the AGM talk, I mean, if you change the scale bar,
It's the
we're
same.
talking about the same thing.
Yes.
I mean, of course,
Yes.
scale up the velocity, the energy, of course, it's different, but
Yeah, here you have relativistic speeds.
sure,
But
not.
in your systems,
Well, they change-
mildly relativistic,
Right.
no?
Only one source.
0.3, 0.5.
Right. It's a few thousand kilometers per second. It's far from the speed of light, but you know, you have a massive object, a disk, a jet, and everything. So
And if you go in X-ray binaries, it's even
Yeah.
more similar and
Right.
interesting to study.
well, I have a few more, but I leave the other people. Thank you very much. It was a very nice talk.
My, well, one of my curiosities was how are the programs for, developing ideas by students funded by the.
We have sponsors and some money they're coming from, for example, ESA, in the Bex campaign, our tickets for the airplane stuff. We have some money from the university. It's not a lot, but but basically from sponsors. We take a lot of stuff to build experiments from companies.
But the group of people who are working on the projects are
Yeah.
looking for their money as well, so.
No,
for
it's
sponsors and
volunteer.
so on, or-
It's volunteer work.
Uh-huh.
We don't get
No, but
paid.
at least, you need funding to buy staff to launch.
Yeah. From
No,
companies, from the university.
My question was, are the students those who are looking for the sponsors as well, or?
Yeah. We have marketing.
Oh, yeah, that's the marketing.
Yeah.
Department. Okay.
So you just talk to companies and say, hey,
Yeah.
would you pay a few €1,000 to put this?
And we have to advertise them to
Sure.
ESA, SSC.
That's a great idea. Proactive students.
Nice.
Actually, it's very optimistic because the budget in Greece is quite low, especially for research, unfortunately.
Right.
And this is fantastic.
And
So
there's also
people outside of academia to give money for
Right.
research.
There's also a company in Greece, software company called Beta, which pretty much gives money to every team in Greece. They're very huge, yeah. And we take with some software that they have, and we use it for our experiments, also with money.
Uh-huh.
It's a little bit of a deal.
Right. I have another question.
Yeah.
Following up on this great effort that you guys are doing. And in just curiosity, can you give us a figure how much did you save about buying cheap detectors and building the box rather than buying expensive detectors?
Okay.
More or less, it's not.
The expensive detectors were like 2,000 euros,
Right.
and we bought sensors with prices ranging from 2 to 50 euros.
Oh,
So the whole experiment cost almost 8,000,
okay.
while a balloon like that can be 30,000 euros. So
Okay.
we dropped it a lot.
And how do the results compare? For example, I have an expectant detector and I have this nice flat curve, and I
Okay.
have the poor detector and it's still flat with big error bars. You know, how do the results compare between the two detectors?
How do they
compare?
compare?
So if I measure you with my tape or if I measure with a proper.
Yeah, I don't know that because actually I was in the thermal subsystem
Right.
there, but it was a big deal that the sensors even worked.
No, yes.
They were supposed to be black, nothing.
Okay.
So
Wow, awesome.
Could you continue of this topic, but I'm curious, just curious. I'd like you to just to comment a little bit more about that's how did you get expressions to take with interferometer?
how do we take?
How did you get that expression of the interferometer element? You talked about
The
beginning
first
maybe expression.
the equation.
If you can just comment a little bit more about the math
From
the maths background, just to,
from here
yes,
to here.
yes. What
Yeah.
is the assumptions you use?
That's a little bit big. There's a big proof for that. So
It's a big problem.
yeah, but
That was the topic of another prize.
Yeah. Simple question.
but I can show you later if you want. We can discuss it later.
Okay.
Yeah, it's typically described in any radio astronomy.
Yeah, I can show it to you.
book. It's like, okay, this is the story.
But it's not simple, right? I mean, I'm not a radio astronomer, but I always realize that this is very difficult, very, very difficult, right?
Actually, I tried to go from here to here with the help of,
You're right.
of my professor. It was very challenging.
But did you succeed? Actually?
I don't know. I think that I managed it, but
I never did it. I tried as well, but I never did.
I think I
You know
still
what?
have
Never
the
tried.
I still have my notes if I can find them.
Okay, more questions, more
I
comments.
have a small question, Giorgos. Do you have an estimation of when the ASTRO
ASTRO.
is gonna be finished?
Yeah.
The
No.
thesis?
Because since it's a project that doesn't participate in campaign, we are going slower, and we are still trying to find some sponsors because radio astronomy is not so popular in Greece. And yeah, we have a lot of students that are first year, second year, and they don't have much experience. So they are learning and they are doing all this stuff. We are do training, so we are going very slow. But maybe in 2 years, 3 years, it will be possible.
What's the radius of the telescope that you guys are planning to do?
5 meters.
5 meters.
5
Oh,
meters.
yeah, you said it. Yeah. Right. Another question I have many, sorry, is that are you talking to all the universities that may have gone through this process to learn from their experience? Or you
Yeah,
are just
unfortunately, we don't have You're referring to ASTRO?
No,
Okay.
I mean, if you have talked, you are in the Thessaloniki
Yeah.
University, have you talked to, I don't know, the University of Oxford or whatever?
Yeah.
You know, to learn from.
For such projects,
Yes.
I mean.
Or you're starting from scratch, like.
Basically from scratch, but
Okay.
we have people that went to these campaigns
Okay.
and they are helping us, that
Mhm.
they are belonging to the team.
Right, right. No, I'm asking this because I was in Chalmers University in Sweden and they have a very similar, they actually
Yeah.
think that it's a bit smaller and it's a ray and it's called Salsa and it's a purely student effort as well. And they're pretty good. I mean, you may want to contact them and say, hey, how did you do it?
Okay.
You know, because they, as I said, they do the remote observations. They have like 6 and a 6 array. The radiant, and I think it's 1 or 2 meters smaller, but they do really interferometry. It's
Yeah.
crazy. And it's purely done by students. So maybe
I've seen papers.
from Salsa,
Yeah.
right? Yes, indeed. But thank you very much. It's very-
Okay, so thank you very much, Jorge.
You know, that's